This talk is called Pushing Kubernetes Forward. I'm going to give a quick background on CoreOS. I have had a few folks come up at the booth, just generally curious what we do and why. So I want to give that quick background just so everyone's on the same page of what our motivations here, why we're in the Kubernetes community. So CoreOS has a small mission. It's secure the internet, so should be done here any day. Started in 2013. We figured it'd take a couple of years, so we should be wrapping that up. But in all seriousness, CoreOS, we started as a Linux operating system, that's where the name comes from. And the idea was to have a really small, modern Linux operating system that did something sort of unique, which was this update itself, and to be read-only in a lot of different ways. So you could do things like a factory reset like you do with your phone by doing the infamous rm-rf/ and rebooting your machine and everything's okay. So it was designed to have kind of updates that are automatic and seamless. And then obviously if we're going to have automatic and seamless updates, which we feel are necessary in order to secure the back end of the internet in a similar way that we've secured our phones and we've secured our browsers, you run into a bit of a problem pretty much immediately, which is that one of these servers is going to decide that, hey, I need to get an update going. I need a reboot, but I have a bunch of work that's actually running here. So I'm going to just reboot and all those apps go away. And without any sort of help of a cluster level system, you're going to have a bad day and you're going to get paged and you're going to hate CoreOS in particular. We don't want you hating CoreOS, so we needed to invent some sort of magical orchestration system that would help do this. Initially, what we did was we built a database called etcd and some other tooling like Fleet to do this orchestration that would help move things around when a machine needed a reboot. Then the reboot would happen and there would be no work there and everyone was fine and you didn't get paged and you're really happy and the work moves back at some point. Now obviously over the last year or so we've been working really heavily inside of Kubernetes as our magical orchestrator here. So about CoreOS, CoreOS Linux was our first motivation. We then built etcd. We had a very talented intern who got a README that said, you need to implement Raft and a key value store over a summer, and he did that pretty well. So etcd is a key value store that we built, and then a container runtime like Rocket. And we have a bunch of other open source projects. And then we also have a number of commercial products, most notably for this community, Tectonic, which is a full platform that's built on top of Kubernetes and a bunch of our open source components. All right, so this talk is going to be product management via a Keynote. As we are an open source community, it's really actually quite difficult to product manage open source communities. So since I have members of the engineering community all around Kubernetes here, people who are using Kubernetes in production, and businesses in the room that are actually building on top of Kubernetes, I thought it'd be a perfect opportunity in order to product manage you all to do exactly what I'd like you to do over this coming release cycle. And kind of talk through essentially what CoreOS is doing and what our motivations are over the next coming release inside of Kubernetes. So these are the major areas that we're pushing forward in Kubernetes in this next release. The first is a simpler to deploy and configure cluster. I think we've all kind of heard the meme over the last day and over the last few months about Kubernetes not being the easiest to deploy. Increasing the scale of clusters throughout the stack. We are really interested in ensuring that Kubernetes is seen and continues to be seen as a very scalable solution. Security based on just good practices. There's a lot of room for improvement inside of Kubernetes and following best practices around key management and certificate authorities, et cetera, et cetera. We would like to have the Rocket engine be an option to power Kubernetes for containerization, which I'll talk about a bit. And finally, standards are extremely important to ensure that Kubernetes continues to give people the consistency and portability that they're looking for, and talk through some of the work that needs to happen inside of Kubernetes and work that's happening inside the community to get us there. So simpler deployments is the first thing. So Kubernetes roughly looks like this in a block diagram. You have etcd, which is the primary data store for Kubernetes, and then you have some control components there that are in the multicolored boxes here in the middle, and then a bunch of scale-out worker machines. And the control components more or less look like this. There's a few applications that have to run and cooperate together in order to do the control side. And then there's, of course, even more, just a couple more few pieces that you have to get running. The DNS add-ons essentially required. You have some things that are essentially providing input into the scheduler. You're going to probably have some sort of networking daemon set that's going to be sitting there helping configure and set up connectivity. And then probably an identity and probably an auth-z service of some sort so that your users aren't just all logging in with the same identity. So it's not really as simple as it looks. There's 6 or 7 or 8 moving parts at any given time in a production-looking Kubernetes cluster. And so the real question is, how do we install it all? So how many of you have done manually placed configuration of Kubernetes where you just scopy files around? Okay, good. And how about cloud config and bash scripts? All right, about a third of the room. And how about some sort of config management like Ansible or Salt or, okay, great. So that's exactly what I expected. We have exactly 3 solutions to this one problem, and we're all kind of just mishing and mashing them all together, and it's really not very satisfactory. And then we end up with this question. Who successfully has a runbook for a Kubernetes upgrade where you feel super confident in it? One person. That guy back there. You're probably lying. I don't know. This is a very complex problem. We have 8 or so different services that are more or less loosely coupled, but kind of critical to our overall infrastructure's health. So we've built a prototype that we called Monocube. My co-founder Alex Polvey built this prototype. The name comes from that Monocube compiles everything that you need to run Kubernetes into a single binary. So you have etcd and then all the control plane services compiled into a single binary. And then the cute thing that Monocube does is it establishes an SSH reverse tunnel out to a set of machines that you specify on the command line. And these machines are booted up to look for a API server on localhost some port. And so what happens is that pretty much every cloud provider, every environment that you end up in, you're going to have some way of getting up to SSH. So our postulate here is that if we get a machine up to SSH, then we have a way of now configuring and deploying a Kubernetes cluster. But it gets a little slightly more complicated. So there's a couple of folks inside of Google and a couple of folks on the CoreOS team that are interested in doing this idea of Kubernetes on Kubernetes or Kubernetes self-hosting, where essentially from this control plane that we have running on our laptop, this kind of single point of failure control plane, we deploy a new control plane that's not talking to any kubelets quite yet on top of those servers. And then we reconfigure, this is currently undefined how this happens, but we reconfigure through some API call the kubelet to kind of reboot itself onto the new API server. And at that point, we have a initial bootstrap of a new cluster. We copy all the state off the laptop, all the etcd state off the laptop into the new etcd cluster that's running on the actual physical gear. And woohoo, we now can pivot from running Monocube to running just kubectl pointing at the servers. So we have a lot of this prototyped out today, but there's a lot of work to go. And so there's a lot of open places for people to help out and start prototyping and give us feedback on whether this idea seems reasonable or sane at all. So this whole process seems really difficult. So what would be the advantages of doing this? The first is obviously that we're down to just SSH, which everyone understands how to bring up. Rolling updates for Kubernetes happens from Kubernetes itself, which is a very satisfying thing. And we have a very great way of managing applications. We should be able to use those same APIs and those same types in order to manage Kubernetes itself. This is a problem that we have quite a bit right now, is that the kubelet is kind of strongly coupled to the version of the kubelet running on the host is pretty strongly coupled to the version on the control plane. And it'd be really fantastic if we could do a rolling update of the kubelet. CoreOS ships the kubelet inside of a container, and we believe that we can start to do this as more of a regular practice for deploying Kubernetes overall. And so my thing here is I want to kick off the discussion around whether this is reasonable, with the goal of us actually getting this into Kubernetes 1.3. All right, this work is happening in the high availability SIG. If you're on the Kubernetes development Slack, please join in and get your opinions and start trying out some of the things that we have working today. Mike Dines in particular from Google has his K8s on K8s repo. That's pretty interesting. All right, so the next bit is increasing scale. We've had a lot of folks in the community concerned about the overall scaling properties of Kubernetes for one reason or the other. And so over the last couple of months, we had a couple of engineers look through the scheduler and figure out where the low-hanging fruit is. So we have a graph that looks really good. I like graphs that look really good. And so this graph is the red line here is the improved work that we did. And the green line is the old version. So this means that the old version of the scheduler, in order to schedule 30,000 pods, took 8,000 something seconds, and the new version took 587 with some caching and some algorithmic improvements, which is like, I'm being very conservative. It's a 10x improvement, but it's roughly a 14x improvement in scheduler throughput. And this was done just as kind of a first pass. We were trying to figure out whether etcd was the bottleneck or the scheduler was the bottleneck. And it's pretty clear that there's a lot of low-hanging fruit in the scheduler today. And so I think there's a lot of ongoing work that we can do. One thing, if somebody, wow, the fonts. If somebody has a interest in doing graphing, we have a lot of data that we're getting out of KubeMark. But it's going to CSVs, and then we're using GNU plot, which generates probably the world's least human-readable graphs, as you can see here. So if anybody has an interest in doing that sort of work, that'd be really helpful for the engineers trying to suss out how to make these improvements. And so, yeah, I think the overall goal here is that we've made good progress in V1.2, and we can probably make similar progress doing a 4 to 10x improvement in the next release if we look around hard enough. So the original kind of theory was that etcd was the bottleneck of Kubernetes. It was pretty clear that that wasn't really the case in a lot of the throughput and latency metrics. And so, but as we started to do these improvements, it became clear that etcd would over time become the bottleneck for us making further improvements and having multiple schedulers operating on top of the Kubernetes state, et cetera. And so over the last few months, we've been working on what we call etcd v3. And this is a pretty big overhaul of the etcd API and improvements to support essentially the Kubernetes workload. The code name is scaling etcd to thousands of nodes. So good code name, pretty clear. And what we're doing first is that we're introducing a new efficient transport based on gRPC. If you're not familiar, gRPC is essentially HTTP2 plus protobuf in a nice, easy-to-use framework that has language bindings in Go, et cetera. We are also introducing new API endpoints that have different semantics in order to better fit with the Kubernetes use case. We'll talk about what we're doing there in a second. We added disk-backed storage. Before etcd was completely in memory storage, which was it was very easy to implement, but also very inefficient when we had lots and lots of keys. We have incremental snapshots because we do have disk-backed storage. We have a lot of what we need already on disk, and so we're able to do essentially incremental snapshots that give more consistent performance when etcd does finally write stuff to disk. We kind of have an envelope of how much I/O and how much time etcd will pause in order to do those snapshots. And then because we have a disk-backed store, we're able to solve this problem that is internal in Kubernetes and really painful. It's this relist problem where the old etcd used to keep a very short history of what happened. You can think of etcd as doing revision tracking of the database at all times. And so it'd be like if Git, you just truncated your history every few days. It's really obnoxious if you come up and you don't have those revisions between when it was truncated and now. And so this relist issue is less of a problem with the new etcd because etcd is able to hold on to hours or days worth of data without having to truncate, because we're not just storing the keys in memory. So some of the cool things here, we introduced the idea of a mini transaction inside of etcd. Kubernetes has been kind of painfully working around the fact that etcd only let you do a transaction on a single key by stuffing a lot of stuff into a single key that might all be related. So with these mini transactions, the internal data store of Kubernetes can be a little bit smarter and only rewrite data that's actually necessary while holding on to locks across multiple keys inside of etcd. So you essentially are able to say, if this is true, then set these new values. We have the ability, because of gRPC and HTTP2, to use a single TLS connection and watch lots of keys and watch those keys over a long period of time as they change. This is how Kubernetes does things like doing the watching of events inside of like kubectl -w. So these watches were really expensive when they were implemented as HTTP 1.1 because, as you know, HTTP 1.1, when you make a connection and do a long poll, as soon as that connection and that request is fulfilled, then the TLS connection is essentially torn down. And so a lot of time and memory and CPU is spent spinning up a TLS connection and tearing it down over and over again in order to fulfill these watches, whereas now we can multiplex a ton of these over a single TLS connection. And the last bit is etcd v2 had TTLs on individual keys. So if you wanted to do a leader election, you essentially had to refresh multiple keys if you were holding on to important data across multiple keys. etcd v3 now lets you do a lease that's held across lots of keys. So if your lease expires, all the data that you were holding on to that asserted that you were leading something can automatically be cleaned up. And then the last thing is we started to prototype a thing called Mirror Maker. So this is the idea of having etcd sitting there with a watch open, and you mirror all the data that's changing inside that etcd into a secondary etcd. This opens up a lot of new interesting possibilities, one of which is that label queries are kind of the new DNS inside of Kubernetes. And what I mean by the new DNS is how many people get paged when there's a problem with DNS inside of their infrastructure. It's never a good day. Never a good day. And similarly, I think as we get more of our applications being cloud native, if we're unable to fulfill an API request for a label query, figuring out where something is within our infrastructure, we're going to have a similarly bad day. And so I'd like to start prototyping out using etcd mirroring so that we can have internal, essentially slightly behind caches of state from the Kubernetes API that can be used by the applications in case the actual API cluster is down, the write through API cluster. Yeah, so we've prototyped out the code on the etcd side, but we haven't done any prototypes on the Kubernetes side for this stuff. All right, so when are we actually going to get done with the v3 release of etcd? Hopefully in the next few weeks to a month and a half or so. The etcd team is really serious about testing. So every time we do a little alpha release of etcd v3, we run it through really rigorous tests. So far, we've ran it through about, at this point, probably about 100,000 iterations of our functional test suite. Each one of the test suites takes a couple of minutes to run. And what it does is it punishes etcd in a variety of ways by stopping traffic, pausing individual machines, causing latency between the machines, just killing individual processes completely, and doing a bunch of just torture tests of etcd. The failure rate over those 100,000 so far has been 0.01%. So we've had one failure, and the team is not pleased with that. So we're continuing testing until we find and suss out a couple more bugs. So they want to wait until we have a few weeks of no bugs before making the initial release of etcd v3. So this was the number it was up to last night after our most recent release. This is at dash.etcd.io if you want to follow along at home. It's quite fun. It goes like all good graphs up and to the right. And then when are we going to do etcd v3 in Kubernetes? Well, we actually already have a prototype pull request up against etcd today. The prototype pull request is mostly to show how bad the abstraction is for the Kubernetes storage layer and all the things that we need to fix up. So a lot of the work is just going to be refactoring the storage layer of Kubernetes initially to take advantage of all the new features in etcd and hopefully get memory consumption and latency. And essentially, it's just better user experience for people using Kubernetes by taking advantage of these new features. But we do have a proof of concept working today. All right. So this is all about increasing scale, all this etcd work. And so again, if you're interested, please get involved in SIG scalability. We have regular meetings where the etcd team and everyone else talks about where the next bottleneck is going to be inside of Kubernetes as we get better and better at this. All right, so this one's pretty fun. Security through identity. Who's familiar with the OpenID Connect standard? Okay, good. It's by far the worst name spec I've ever encountered in my life. They thought that they would like ride on the success of OpenID, which is an utter failure, and then combine that with the complexity and confusion around OAuth 2.0, which is completely different than OAuth 1. And so just combined, it just makes a very solid marketing message of, I don't know. And so we built a OpenID Connect provider called Dex. It's open source and based on OpenID Connect, which you can think of OpenID Connect as essentially OAuth 2 with types. OAuth 2 is very loose on how anything worked. And so OIDC comes through and actually cleans it up so that somebody can walk from beginning to end and implement something that multiple clients can work on without having to have like provider-specific information. Dex has a number of ways of backing this OIDC protocol. You can have usernames and passwords in the database. It can back LDAP. Recently, a company in Europe added LDAP support, which was great. And we have lots of other connectors too. And the great thing about OIDC is you can chain infinitely your identity. So you could have Dex backed by Google, backed by Facebook, backed by Twitter, backed by Dex by Google. So you can also do kind of these arbitrary chainings. So the whole project, the whole Dex project is applicable outside of Kubernetes, but our use case and why we built it was primarily around wanting to get it inside of Kubernetes. In fact, if you go to tectonic.com and sign up for the free starter version of Tectonic, you're going through Dex. The whole identity of tectonic.com is OIDC based. Right. So what we've done so far is we've got the OIDC. We've got the Kubernetes API server aware of OIDC. So if you pass in a token in an HTTP request and configure the API server to, say, parse out the OIDC token that's passed in, it's just a token that's in the authorization header. Kubernetes will actually parse that out and start to give that metadata to other pieces of the Kubernetes control plane. So in this case, for OIDC, Kubernetes is the relying party, essentially the application. The end user is the human being who's trying to get into Kubernetes or use kubectl. And then the identity provider is Dex. So, or it could be Facebook, or it could be Google. So you could, back your Kubernetes cluster by Facebook, so all your friends could use it. In this case, we'll just talk through Dex. But the whole idea here is that Kubernetes and Dex, they are constantly exchanging a public key. So this public key is being cycled on a configurable time, but every 12 hours, essentially, Dex generates a new key. And so they synchronize this key, this short-lived key, every 12 hours. And then when somebody comes through and they want to log in, they say, I want to try to get into Kubernetes. The user is redirected to the auth page that's hosted by Dex. They get cookied. They send their grant off to Kubernetes, and then they exchange. Kubernetes exchanges the code for an actual identity token that has some timeout on it. And so it's just a really straightforward OAuth flow if you're familiar with it at all. And what the token actually is this thing called a JWT, and it looks like this. It's essentially a dot-separated set of base64 encoded JSON. And so you have like some information about the algorithm, and then what's really important is that you get information about the user. So you get like, say, their email address, and then maybe some groups that they belong to inside of the cluster, and then their name and a unique identifier. And so what we're doing is that the API server now has the ability to extract user data by a login into DEX. Primarily a username and a group is what we're interested in for the context of Kubernetes. But there's really not much that we can do with this group information quite yet, except for recently and in the Kubernetes v1.2 release, we added a webhook authorizer. So you'll be able to have Kubernetes configured to talk to another service inside of the cluster. That service will get some JSON that has all the OIDC information and say, is this person authorized to do whatever action they're trying to take? And the authorization server will say yes or no, and that will be a complete flow. So we'll be able to have the secure cryptographic identity that is held inside of a central identity provider that can be federated across an entire organization, and Kubernetes is able to take that information and then make yes or no decisions on whether people are able to access things outside of certain namespaces they've been assigned to, et cetera, et cetera. So that's security just through identity of individuals using OIDC inside of Kubernetes. This work hasn't been completed because we've only gotten part of it. For example, kubectl today can't do OIDC, and this is because of the need for Kubernetes to do refreshing of tokens on the back end. And so we'll probably get that work into v1.3. But we have a pretty good start with the authorization stuff and the work that we've done to get the basics of OIDC into Kubernetes. It's pretty exciting work because it means that a lot of people who are using Google at work, or they have other OAuth or OIDC providers that they can just use off the shelf, they can back their identities inside of the Kubernetes clusters without having to kind of have a separate set of identities or having a Git repo with JSON objects that say who has access to what. All right, so this next one is Rocket Powered Kubernetes. So Kubernetes has made it to 1.2 with only having one container engine, the Docker engine that it supports. And so I jokingly say that we're doing a mid-flight engine swap inside of Kubernetes to support a new container engine. We've done a lot of work to essentially refactor the internals of Kubernetes to be more abstract and be able to support new container engines. And if you're not familiar, Rocket is a new container runtime that we introduced about 15 months ago. A bunch of the developers in the room, actually, who've worked on Rocket. Can I get a shout out from Iago and Alban and John? Get off your phone, John. Hey, John. It's a really simple composable tool. It doesn't have a lot of moving parts to it. And it's focused on, this must have been me about 4 a.m. last night. It's focused on essentially, it's focused on providing a lot of the abstraction that Kubernetes provides. So Rocket, for example, has pods as a first-class citizen, and that becomes important as we start to talk about some of the interesting other features Rocket can do, such as run pods inside of virtual machines. So Rocket has no central daemon, has no mandatory API. The API that it does present is optional and can be essentially as a read-only API to assist Kubernetes in getting data faster and caching that data. And apps run directly into their spawning process since there is no central execution daemon of Rocket. So if you run Rocket, it's like you execute Rocket and then the application executes directly underneath it. So if you have an init system or something, it just executes in the process tree. It has this kind of modular architecture that we take advantage of by doing things like executing pods inside of VMs. We also have built things like CNI, which is the container networking interface that's used inside of Kubernetes, is also used inside of Rocket. And so it just kind of takes care of a bunch of the details and tries to provide a nice clean abstraction for just taking some container images and running them in various ways. So Rocketenetes today, that's what we call Rocket plus Kubernetes, is nearly complete. We have 80% of the end-to-end tests passing. Last week was very unfortunate for the Rocketenetes team because they got 5 new tests passing, and then Kubernetes added 5 new failing tests for Rocketettes, so it was a complete wash. The engineering team was a bit crushed, but the work is going along quite nicely. The next big hurdle is that we're adding C advisor support so that we can get information about C groups and stuff into the rest of Kubernetes that Rocket is managing. Live demo. All right, so you're going to have to wish me luck on this one. What we're going to do here is look at a live running Rocketettes cluster that is up on GCE. And it's running the guestbook application. So we can see it's actually running here. Woohoo. Let's see if... well, looks like networking went out. So what we'll do is we'll just look at the machines and kind of get a sense of like what Rocket does slightly differently. So let me Alt-tab over this. All right, so what we're doing is I have this cluster running up on top of Google Cloud. We have some various nodes that are running here. So if I'll go ahead and SSH into these one of these machines, and we'll just take a look at compute. And we'll take a look at what's slightly different about Rocket versus the Docker engine. So the first thing is that Rocket does first-class integration with systemd. If you haven't used systemd, you'll have to use it sometime in the future because every Linux distro uses it now. So congrats on that. So what we're gonna do is there's a system inside of systemd called machined, which is essentially a place for containers to register themselves. And so each of the Rocket containers that are running on top of here register themselves with systemd. The nice thing here is that because they're registered with systemd, we can actually start to pull out the logs. The logs get integrated with the systemd journal. So we can see all the logs. It looks like this is the kubedns API endpoint that's going in here. And so anything that is journal aware, which lots of stuff is, like things that are able to push off logs to log aggregation systems, you're able to push off all your Kubernetes logs and all of your system level logs essentially from one central source on the server. The other thing is we'll also just do a sanity check here and see that the Docker service is not running. So everything that is necessary for this Kubernetes cluster worker node is completely running inside of Rocket. So the reason my demo is not working is because I'm also running from master, and there's a regression in hairpin NAT in master over the last couple days, causing flaky tests. So yay for running master. All right. So the next step here. So the goal for v1.3 of Kubernetes is to have 100% end-to-end test passing and working inside of Kubernetes. I think that's pretty attainable at this point. What we're down to is just a lot of noise. All the basic stuff works. Most nearly all the examples inside of the examples directory in Kubernetes works. We're getting down to stuff like things assuming Docker logs and stuff failing. The overall like acceptance criteria is that we want to make sure that most users are able to move over to Rocketettes without any real regressions that are noticeable or unexpected. Right. All right. All this work is happening inside of SIG-Node. The folks in there are doing a lot of the work to ensure that we introduce good abstractions that can be used later on by new container engines. And this has been a lot of why the work has taken so long. It's always once you add the second system that you realize how terrible your abstraction was the first time. When we started this work, the Kubernetes team was like, oh, we made an abstraction. I'm like, So we started looking at the abstraction, and it essentially was a one-to-one mapping of the Docker interface, which is not an abstraction. That's copying and pasting. So there's a lot of work going on there, and it's going along quite nicely. So the next bit I want to talk through was security. We have been doing a bunch of stuff around TPMs recently. If you're not familiar, TPMs are a trusted platform module. one of our engineers, Matthew Garrett, will be giving a talk later in depth on this. But essentially, it's a physical chip on your computer. Most servers ship with it today, or it's a like 40-cent option for the overall cost. And the idea is that you have like a burnt-in cryptographic key, hardware key in the server. And then it has a bunch of ways of essentially measuring whether the system's coming up into a known state. It's historically been used just to measure the bootloader and the OS, but what we want to do is bring that up all the way into the application space inside of Kubernetes. So what we've done so far is Matthew has done a lot of fun work, such as patching GNU Grub. He's a member of the Free Software Foundation board, so that's, I guess, part of what he likes to do, is patching up GNU Grub to support this work. And then we've added support into Rocket so that as Rocket is launching containers, it records a JSON object about the stuff that's going into that container and the images that are being executed. And we run that through the TPM and generate hashes of that. The overall idea is that we're able to later on attest that and understand exactly what executed through the Rocket engine at a cryptographic level that's verifiable externally from the host. So it looks essentially like this, is that we start at the very bottom. The user has control of both secure boot keys and the keys of the TPM. The secure boot bit of the system verifies the actual integrity of the OS, and then we measure that and put it into the TPM. And then it goes further up the stack, essentially to the point that we start writing and writing through logs about what actual containers are executing. And then inside of our distribution of Kubernetes that we call Tectonic, we are bringing that trust all the way up to Kubernetes so that as machines are executing containers, the nodes that are actually attesting and actually have a verified log and they're executing what they're supposed to be executing are allowed to join into the cluster is the overall goal there. Initially, it's going to be advisory, like showing people, well, this is what your systems are executing, but then over time, we'll be able to help them tune those down so they can say, if they're executing things that I'm not expecting in this set, then they need to be ejected from the cluster. If you're interested in that, we have a blog post on it. It's called CoreOS Trusted Computing. The basic idea is that, as we know, the kubelets write up to the API server every X period. I think is really fast right now. It's on the order of seconds. But the idea is that this heartbeat that we're already doing through the kubelet, we would add into that heartbeat a signature of a verifiable signature that attests what the cluster is doing or what the machines are doing. And so the overall goal here is that we're able to append this payload information inside of the heartbeat into v13. We already have all of this code written for the most part. It's about getting it upstream in an acceptable state for everyone. Yep. So if you're interested in this, Matthew is much more articulate on why this is important and how it all works. His talk is at 11:30 today. All right, the next bit is TLS Bootstrap. So today, a lot of how the nodes inside of the cluster are configured, at least the default for a lot of people, is either completely unsecured and unverified connections between the kubelet and the control plane, or people manage a certificate authority, and for the most part, they have one cert that's used by all the workers, and then one certificate authority that's managed by the API server. So one thing that we're interested in doing, and we have a proposal up, but we haven't finished the code for, is making it so that individual nodes can generate a certificate signing request, submit that to the API server, and say, hey, I'm a new node. Do you approve me or not? And this would go into an approval queue that either a system administrator can say, yes, this node's allowed to join the cluster and get access to my secrets and the workload on that cluster, or you could imagine some sort of automated system that checks with your cloud provider API and says, well, this is a legitimate machine that actually I see inside the inventory. It's coming from an IP address that I trust. It's good enough, accept. So you can imagine essentially a few different modes that we've written out in the proposal so far. And so this is essentially a pretty important piece of generating a trustable infrastructure, is being able to have tight control over who's joining and having control over a list of people who have been removed permanently. The hope here is to get this the proposal merged into v1.3 and hopefully a completely working version of the API as well. All right. So the last bit is that we talked about this a bit yesterday too, is that there's a lot of industry movement around cloud native and around containers, et cetera, et cetera. And as part of this industry movement, we've created a couple of different foundations and initiatives. So anyone have a crisp explanation and a few words of what these two things do and how they're completely different? All right, so just so we're clear, I just want to go over this, and it's pretty important. So the Cloud Native Computing Foundation is a place to coordinate the promotion of cloud native architectures. We talked about this yesterday, and a home for projects that are cloud native, such as Kubernetes. And it has a technical board that helps to make these decisions and helps articulate the message. It also provides a bunch of shared resources like compute and video conferencing, et cetera, essentially a little bit of a framework for people to get their work done. The Open Container Initiative is much more narrow goal. So the Open Container Initiative is about creating technical standards for containers. It doesn't start to talk about clustering. It doesn't start to talk about a lot of the things that we're here interested in this conference, but it nonetheless is a very important piece. I think we all realize that things like Kubernetes and all this technology wouldn't really be possible if we didn't have a container image that we could ship around. And so the Open Container Initiative started 8 months ago with RunC, which was a project that was started by Docker, and a runtime specification, which said, how do I take a set of files on disk and execute them in a namespace in C group? But there's also a large mandate from our entire industry and from many of our users and from everyone overall that we need to standardize an image format. The thing that we think of today is a Docker image. Essentially, how do I take a set of files, put them up on the internet, give them a name, and then tell somebody else on the other side of the globe that they can download it, and that same thing will come down to their system, and they'll be extracted, and they'll have those exact same files ready to be executed. So over the last 8 months, we haven't really accomplished this goal quite yet. This work is in progress, and I'm quite hopeful that we'll get to a place where we do have a shared standard that can be implemented kind of independently and with confidence across the industry. Essentially, I think this work is important because it'd be quite a shame if we end up with wasting the tens of thousands or hundreds of thousands, or I don't even want to think of how much time's been wasted and effort on deb versus RPM. I think we've all been there and written a control file and a spec file and hated our lives. So the overall goal is to create less hate and to create a place where we can just all come together and agree about how a tarball with some JSON files comes together and is shipped over the internet. All right. And along with this work, one of the necessary things is that we're going to have to have inside of the v1.3 API a way of handling image formats. So we've had a bunch of different things that we want to do. One of them obviously is the OCI image format. But we've also had things that we've been talking about, such as like just plain tars that come out of your Jenkins or your CI system. Maybe Kubernetes will just execute a jar one day. I don't know. I think that would be an interesting discussion. Or just a Go binary. So you put a Go binary up or a static binary up on a HTTP endpoint, and Kubernetes downloads it and executes it inside of its container engine. And then the last bit is that we haven't really tackled the problem inside of the API of signing and content verification. This is pretty obvious thing that we should be doing, and we haven't really done it quite yet. All right, so my overall thesis here is that you are all fully indoctrinated with the goals that I have in mind over the next quarter inside of Kubernetes, and you want to help me push this all along. So just as a review, we want to get to a point where Kubernetes is simple to deploy, and our hope that is by starting with SSH and some new code inside of the kubelet that we can get there. We want to continue to increase the scale of Kubernetes, and we're doing that work through etcd v3. The best way that people can get involved there is by kicking the tires on v3. We've gotten a lot of good feedback. There's a developer from NTT who's in the room who's been giving us a lot of great feedback, and more is necessary in order to make sure we don't mess it up. It takes a lot of different points of view to not mess up things like an API. Just doing best practices around security. We have a pretty good foundation. We're using TLS in all the right places inside of Kubernetes, but there are a lot of things that we could be doing better, particularly around onboarding of the worker machines. Getting the Rocket engine in is really important, and one of the best ways in order for us to ensure that the Rocket engine is doing well, besides the end-to-end tests, is having users actually test it out and figure out where the problems are, where the applications are breaking, if there's images that aren't working, etc. So there are instructions that we have. If you Google Rocket plus Kubernetes, you'll hit a CoreOS page that has a Google Doc that has a burn down list, and then how to get started on GCE of how to try out Rocketettes from master. So maybe you can help debug this hairpin issue that's happening in master at the moment. And then the last bit is that we need standards in order to ensure a healthy ecosystem, and that portability continues to happen across different environments. So overall, I just want to end with, I think that Kubernetes is a great, exciting technology, and I feel like this most days when I'm working on it, or I have to interact with our production environments. Just so pumped about operations again. It's been a long time since I've been excited about operational software. Last, I would like to invite you all to our conference in Berlin in May. It's CoreOS Fest. It's a celebration and a conversation around open source software that we've been building and how people are using it inside of their projects, inside of their companies. And we're also accepting papers if anyone has been using this technology and would like to talk about it. And with that, I will end and take a couple questions maybe, and I appreciate your attention. Thank you.
Any questions?
Yeah, if you want to yell it out, I'll just repeat it. Yeah.
Can you please comment your thoughts on the networking side of things in OCI and how, for example, adoption of things like CNI embedding that with Kubernetes or aligning with the CNI effort in Kubernetes with the one in OCI? So we have a full-based container engine as a standard.
That's a great question. So the question was about if the OCI is doing anything about container networking and how that plays in. So the OCI has decided on a way of executing plugins around a single process, and this essentially plays exactly into how CNI works today. So with a very trivial few lines of essentially bash script, you should be able to adapt any CNI plugin to be an OCI plugin. And so the model fits quite nicely, and I don't think there's going to be any problem with doing that. I haven't had any really discussions about whether the OCI wants to take particular plugins as a standard or particular plugin architectures. We have been having discussions about the CNCF taking CNI and making that part of that organization. Because the CNI is more about a bunch of code for setting up Linux networks and then a spec. So it's more a combination of the two, and that's why we're thinking CNCF. But I'd love to have that discussion with you if you're interested.
Another question? We've got one, maybe two more. Wow.
Great.
You've covered it. Oh.
This may be a little bit of a controversial question, but what is Docker's stance or opinion about the mission you guys are embarking on in terms of trying to secure this? Right? It's funny, but it's true, right? Because we constantly read about this, and so we're all kind of curious as to if Kubernetes is standardizing, or at least started off with the Docker image format and everything around Docker, how this is going to evolve to include other runtimes, and what is Docker putting into it to ensure that?
Sure. So when we started the Rocket project, at the time, the Docker image format, the V1 format at the time, wasn't well prepared for being a secure format. I think that was pretty well understood through the industry. So the AppC image that we introduced had a content addressable image, had the ability to sign those images. And over time, Docker's V2 image has gotten the ability to do similar things over the last year. So I think they have similar engineering goals as far as making sure that these image formats are well built with good practices. I think it's important for us as an industry to end up in a point where there is a not just an image format implemented by each of the things, but an actual spec that people can sit down and read from top to bottom. And what I really want to see is a spec that people can read from top to bottom and build new build tools around. The Docker file is a great way of getting started, but it's insufficient for just thousands of use cases where you want to generate minimal containers or you want to integrate with existing things. Or the thing that I really want to see is builds that happen completely in user space. So you can start to think of container builds as being a job running in Kubernetes completely untrusted that's just transforming source code into a tarball. So I feel like overall the Docker team has been doing the appropriate work in order to move the format forward. I just want to end up in a spot where we have a format that's actually shared and that people have in good faith and in good confidence are able to implement. And I think that's why it's important that we do this inside the OCI. Yep.
Fantastic. Thank you, Brendan. I think we're running out of time for the moment.
No worries. Thank you so much.
Thank you.